We used to only know about the planets that circled around our sun, but now we know that there are rocky worlds and huge gas clouds that circle other stars. They have a great story to tell. The early history of these planets would have been very, very violent. Planets are made the same way everywhere. They come from the dust and other things that are left over after stars are born. So if they're all made the same way, what makes them so different? As it turns out, the universe is full of galaxies, gas clouds, stars, and planets. There are 8 worlds in our sun system, but now we know that they are just a small part of the huge family of planets in the sky. It's a very important moment in the history of science to be sure that there are other systems of planets out there. In our Milky Way galaxy, which has 200 billion stars, there are probably dozens of planets. NASA sent the Kepler Space Telescope out into space in 2009 on a 6-year mission to find new planets that orbit other stars. So far, they have found more than 400. Some are huge spinning balls of gas that are 5 times as big as Jupiter, while others are huge rocky worlds many times larger than Earth. Some follow wild erratic orbits, so close to a star that they're burning up. One thing is clear. No 2 planets are the same. Each one is unique. But most of these new worlds are very far away and hard to study. Most of what we know about how planets work comes from the 8 planets that circle our sun. Our own planets come in 2 main types. There are 4 rocky planets in the inner solar system: Mercury, Venus, Earth, and Mars. In the outer solar system, there are 4 giant gas planets: Jupiter, Saturn, Uranus, and Neptune. Each of the 8 worlds is very different from the other 7. When our solar system was born 4.6 billion years ago, they started to develop their own personalities. When the sun ignited, it released a massive cloud of gas and dust into space. All 8 planets, including the metal planets closer to the sun and the gas planets farther away, came from this cloud of space debris. All of the worlds in our solar system are made of the same materials. They're made from the same cloud of gas and dust. However, they formed under very different conditions. Some of them formed close to the sun, where it was much hotter, and some formed far away, where it was much colder. And since the situations were so different, the things that came out of them were also different. So at the beginning of the solar system, there was a pretty even mix of silicates, water vapor, hydrogen, a lot of hydrogen, methane, and other things. These elements in the dust cloud are like ingredients in a cake. They cook in different ways based on how the ingredients are mixed and how hot the oven is. Just like you did with the cake, then you put it in the oven and bake it, and it would change. So, basically, this is what happened in the solar system. Overall, the planet cooks in a slightly different way depending on how close it is to the sun. Near the sun, where it is hot, gases are burned off, and water boiled away. Only materials that stay solid at high temperatures, like metals and rocks, can survive. This is why only rocky planets form close to the sun. As a planet moves farther away from the sun, it cooks in a different way. But what kind of planets will form depends on what's in the cloud. Based on what kind of cloud a solar system forms in, it might not have any rocky planets because it didn't have enough materials to make something like Earth. Instead, it might have more gas giants or none at all. If you want planets that are made of rock, you need a cloud full of metals and rocks. The next step is to turn down the heat. As it cools, some of the things in it that have a high boiling point start to condense out as solids, and these very small mineral grains can start to form. These tiny pieces of rock and minerals are the beginnings of a new rocky world. They start to stick together over time. If you had one dust molecule and another dust molecule, they would basically hit each other and make one slightly bigger dust molecule, and they keep getting more and more. This process is called accretion. As these things got bigger, they became basically rocks. Then rocks slam into other rocks and form boulders. Boulders smash together to form bigger boulders. At some point, you'll have something big enough that its weight is strong enough to start pulling things towards it. So instead of just crashing into things and getting bigger that way, it was actively pulling things in. At first, there were a lot of young planets in our own solar system. maybe 100. Asteroid belt and look at the asteroid 4 Vesta, you can get a good idea of how big a hard planet has to be before it can pull itself into a sphere shape. Vesta is only 329 miles across, which isn't quite big enough to be a sphere. To become round, a growing planet needs to be 500 miles across. Then it has enough gravity to crush it into a sphere. Any smaller, and it stays in a regular shape. Every time a round baby planet crashes into something, it makes it hotter and hotter until it starts to melt. Gravity is now starting to sort the heavy things from the lighter ones. Lighter things tend to float up and form a crusty layer, while heavy things, like most metals, fall down and form a much denser core at the planet's center. Finally, the young planets are starting to look like planets, but now they have to make it through a time of violence and destruction, a cruel time that will decide which planets will live and which will die. After the sun was made, all 8 of our planets came from the same cloud of dust and gas, but they turned out to be very different. There was no real plan for how each of the new planets should be made. They did follow the rules of physics and chemistry, but most of what happened was just a matter of luck. About 4.5 billion years ago, our sun was surrounded by about 100 young planets. It turned into a demolition derby. Planet hit planet, and most were wiped out. The early history of these planets would have been very, very violent, with many of these collisions happening in the last stages of each planet's growth. As these collisions happened and things ran into each other, some of the planetesimals started to grow at the expense of the others, and these things that would eventually become planets grew and grew. As they got bigger, they sucked up all the smaller planetesimals around them, which caused a lot of space debris to hit the surface of the protoplanet. After it was over, there were only 4 different rocky planets left. Because of the things that happened to each planet in the past, they are all so different from each other. Mars is a frozen wasteland. Earth flows with liquid water, Venus is a place full of volcanoes, and Mercury is small, empty, and very hot. Because of a huge crash, Mercury, for example, has a very thin crust and is very dense, so it could have been a bigger planet in the past. Then something hit it at an angle, which tore off the lighter crust and left only the dense center. Also hit hard was the young Earth. At the end of the Earth's development, it was hit by something else, which tore apart its mantle and sent the pieces into orbit around the Earth, where they regathered to form the Moon. Something also seems to have crashed into Mars. The crust of the Earth is thinner in the north than in the south. One idea about what might have caused this is that the northern hemisphere of Mars was hit by something early in the planet's history, which blew off a lot of its crust, and that crust started to build up again. In the south of Mars, there were 2 effects of all these collisions. They cut down on the number of baby planets that were still alive, and they brought more ingredients to the survivors. If you had a collision with something that was metal-rich, those chunks would tend to descend down into what was becoming the core, whereas if you collided with something light or icy, they would tend to just float about and form part of the crust instead. Near the Sun, there were 4 rocky planets that were almost done. They were made of a solid core of hot iron, surrounded by a layer of liquid iron and a shell of molten rock. On top of that is a crust on the surface. All of these rocky planets were made the same way, from the same basic materials, but each of them was very different in size and destiny. Space may look empty, but it's not. It's full of stuff blown out of the sun. Strong magnetic fields are made by the sun. These fields rise up in giant loops above the surface. When they hit each other, a storm of very hot, very charged particles shoots out into space. The name for it is the solar wind. Astronauts can see it from space, but only when they close their eyes. When you close your eyes, you sometimes see a little flash, and that flash of light is caused by an energetic particle going through your head and interacting with the fluid in your eye. You see one of these every few minutes. Solar wind could kill the astronauts if they were exposed to a lot more of it. During the Apollo program, there was an explosion on the sun between 2 moon missions that would have killed the astronauts if they were there. But here on Earth, radiation the solar wind doesn't pose much of a threat because we are protected by an invisible magnetic field that comes from the center of the Earth. You can make magnetic fields from motion by converting the energy of the motion into magnetic energy. Deep inside the Earth, the same thing happens as the Earth spins, the hot liquid metal. Just like you did with the cake, then you put it in the oven and bake it, and it would change. So basically, this is what happened in the solar system. Overall, the planet cooks in a slightly different way depending on how close it is to the sun. Near the sun, where it is hot, gases are burned off and water is boiled away. Only materials that stay solid at high temperatures, like metals and rocks, can survive. This is why only rocky planets form close to the sun. As a planet moves farther away from the sun, it cooks in a different way. But what kind of planets will form depends on what's in the cloud. Based on what kind of cloud a solar system forms in, it might not have any rocky planets because it didn't have enough materials to make something like Earth. Instead, it might have more gas giants or none at all. If you want planets that are made of rock, you need a cloud full of metals and rocks. The next step is to turn down the heat. As it cools, some of the things in it that have a high boiling point start to condense out as solids. These very small mineral grains can start to form, and these tiny pieces of rock and minerals are the beginnings of a new rocky world. They start to stick together over time. If you had one dust molecule and another dust molecule, they would basically hit each other and make one slightly bigger dust molecule, and they keep getting more and more. This process is called accretion. As these things got bigger, they became basically rocks. Then rocks slam into other rocks and form boulders. Boulders smash together to form bigger boulders. At some point, you'll have something big enough that its weight is strong enough to start pulling things towards it. So instead of just crashing into things and getting bigger that way, it was actively pulling things in. At first, there were a lot of young planets in our own solar system, maybe 100. Most of them didn't make it. If you go to the asteroid belt and look at the asteroid for Vesta, you can get a good idea of how big a hard planet has to be before it can pull itself into a spherical shape. Vesta is only 329 miles across, which isn't quite big enough to be a sphere. To become round, a growing planet needs to be 500 miles across. Then it has enough gravity to crush it into a sphere. Any smaller, and it stays in an irregular shape. Every time a round baby planet crashes into something, it makes it hotter and hotter until it starts to melt. Gravity is now starting to sort the heavy things from the lighter ones. Lighter things tend to float up and form a crusty layer, while heavy things like most metals fall down and form a much denser core at the planet's center. Finally, the young planet's R flows around the solid core, turning its energy into a magnetic field that comes out of the poles. It keeps the solar wind from getting into the atmosphere of the planet. And if the planet has a magnetic field, the magnetic field will send the solar wind around the planet. The solar wind is pushed away from Earth by the magnetic field, which protects the atmosphere and everything on the surface. Big storms of solar radiation can sometimes mix up the magnetic field. Then big light shows called auroras happen over the poles. Without a magnetic force field, Earth's atmosphere and water would be blown away by the solar wind, leaving a planet that is dead and dry, a lot like Mars. Mars was made the same way Earth was, but today it's cold and dry, and there's not much going on. So why have the two planets changed so much? NASA sent 2 robots to Mars in 2004 to find out what was there of the Spirit and Opportunity rovers. They looked at miles of the surface of Mars and proved that Mars is a dry, dangerous desert with only a thin atmosphere. But they did find signs that water used to be there. Mars wasn't always a dry, barren place. We have found strong evidence that water was once below the surface, rose to the surface, and evaporated away. In a few places, we can also see ripples that are made when water flows over sand. So not only was there water under the ground, it had flowed across the surface. If Mars used to have water, it probably also had a lot of atmosphere around it. So what happened? We can see that there were volcanoes on Mars in the past, so it had a hot interior at some point. And because it was made of the same stuff as Earth, it would have had a hot iron core surrounded by liquid metal. In the middle, it should have also had a magnetic field. Early in the planet's history, Mars apparently had a strong magnetic field, and it was probably caused in the same way as it is astronomers have found more than 400 new planets in solar systems far away. Almost every one of them is huge and made of gas. Our solar system has four of these so-called gas giants: Jupiter, Saturn, Uranus, and Neptune, all of which have thick, soupy atmospheres with lots of hydrogen, helium, and methane. Why are these outer four made of gas when the inner ones are rocky? It's very cold here, 500 million miles from the sun. At the start of the solar system, there was some dust but mostly gas and water frozen in ice grains. It was cold enough to make solid snow where the big planets began to form. We think that we were able to make ice snowflakes and that these were able to stick together to form the cores of the giant planets. We think that's why the big planets might have grown so big, because there was so much ice and gas. Their cores grew to be about 10 times the size of Earth. A lot of gravity came from these big cores. They had so much pull that they sucked in all the gas around them and made thick, soupy atmospheres that went down tens of thousands of miles. The more gravity they made, the bigger they got. More and more dust and debris kept getting pulled towards the planets, and this is what made up their moons. Each of Jupiter and Saturn has more than 60 moons. The gas planets have something else that makes them unique: rings. Saturn is different from the other planets because it has these beautiful rings. It turns out that Jupiter, Uranus, and Neptune also have rings, but they are very weak and hard to find. But they are there. There are rings around all four of the gas giants, but Saturn's are the most obvious. From far away, Saturn's rings look like a single flat disk, but in reality, they are made up of thousands of small rings that are only a few miles wide each. When the Cassini probe flew by, it found that billions of pieces of ice and space debris were moving around inside the rings at up to 50,000 miles per hour. These pieces of ice and rock hit each other all the time. Some of them turn into small moons, some of them fall apart. But they never grow bigger because Saturn's huge gravity pulls them apart. Scientists are just now starting to figure out how the rings came to be. The idea is that a comet hit a moon and knocked it out of its orbit, bringing it closer to the planet. Saturn's gravity tore it to pieces, and all of that stuff got stuck in rings that went around the planet. But the real mysteries of the gas giants are deep inside them, ends of just like you did with the cake. Then you put it in the oven and bake it, and it would change. So basically, this is what happened in the solar system overall. The planet cooks in a slightly different way depending on how close it is to the sun. Near the sun, where it is hot, gases are burned off and water boiled away. Only materials that stay solid at high temperatures, like metals and rocks, can survive. This is why only rocky planets form close to the sun. As a planet moves farther away from the sun, it cooks in a different way. But what kind of planets will form depends on what's in the cloud. Based on what kind of cloud a solar system forms in, it might not have any rocky planets because it didn't have enough materials to make something like Earth. Instead, it might have more gas giants and none at all. If you want planets that are made of rock, you need a cloud full of metals and rocks. The next step is to turn down the heat. As it cools, some of the things in it that have a high boiling point start to condense out as solids. And these very small mineral grains can start to form. These tiny pieces of rock and minerals are the beginnings of a new rocky world. They start to stick together over time. If you had one dust molecule and another dust molecule, they would basically hit each other and make one slightly bigger dust molecule. And they keep getting more and more. This process is called accretion. As these things got bigger, they became basically rocks. Then rocks slam into other rocks and form boulders. Boulders smash together to form bigger boulders. At some point, you'll have something big enough that its weight is strong enough to start pulling things towards it. So instead of just crashing into things and getting bigger that way, it was actively pulling things in. At first, there were a lot of young planets in our own solar system, maybe 100. Most of them didn't make it. If you go to the asteroid belt and look at the asteroid 4 Vesta, you can get a good idea of how big a hard planet has to be before it can pull itself into a sphere shape. Vesta is only 329 miles across, which isn't quite big enough to be a sphere. To become round, a growing planet needs to be 500 miles across. Then it has enough gravity to crush it into a sphere. Any smaller, and it stays crashes into something. It makes it hotter and hotter until it starts to melt. Gravity is now starting to sort the heavy things from the lighter ones. Lighter things tend to float up and form a crusty layer, while heavy things like most metals fall down and form a much denser core at the planet's center. Finally, the young planets are thousands of miles below the clouds. Here's where things really get going. It's a place so extreme that it goes against the natural laws. Most of the new planets we find orbiting faraway stars are huge gas planets. They are so big that Jupiter seems small next to them. But nobody knows what happens inside gas giant planets, whether they are in our solar system or far away. We know that Jupiter's thick atmosphere goes down 40,000 miles, and we can see bands of gas moving at high speeds that make violent storms on its surface. But we don't know what's happening inside, far below the storms. NASA sent the Galileo spacecraft on a 14-year trip to Jupiter to find out. On December 7, 1995, Galileo sent a probe into Jupiter's atmosphere, which it did at a speed of 160,000 miles per hour. As it fell through the thick air, the parachute slowed it down. It saw lightning in the clouds and 450-mile-per-hour winds. The probe transmitted data back to Earth for 58 minutes. What happened to the Galileo probe that we dropped in? It didn't hit anything. It just kept falling into Jupiter's environment, and the pressure kept going up and up and up. As it fell, it measured pressures 23 times higher than on Earth and temperatures over 300 degrees higher than on Earth. When you're in the environment of a gas giant and you go deeper and deeper into the soup of hydrogen, which has no solid surface, it can still be very heavy. And so, eventually, you would be crushed by the overlying weight of the material that's there. Even though the probe only went 124 miles down before it was crushed, it showed scientists what Jupiter's inside looked like. But the dark heart of the planet still remains a mystery. Like some rocky planets, the gas giants have a magnetic field too. Jupiter's magnetic field is 20,000 times stronger than Earth's and so big that it goes all the way to Saturn, which is more than 400 million miles away. Planets don't have iron cores that get very hot. They formed around frozen cores of dust and ice, so we don't really know what's going on inside. We really don't know what makes up the deepest parts of Jupiter's interior, so it's possible that Jupiter has a solid core at its center, or it could just still be liquid. We might never know since no probe could ever go the 44,000 miles to the center of the planet to look into it. Galileo was destroyed before it could reach the center of the planet. Gravity and heat shape how planets evolve from their inner cores to their outer atmospheres. They're the great creative forces in planet building. But there's one more thing that has a big effect on how planets turn out, and that ingredient is water. Planets may look like they are fixed and don't change, but they are always changing. One planet in our solar system lost its atmosphere and turned into a desert. Another planet got too hot and changed into the planet from hell. Planet Earth has also changed, and it was water that changed the game. When you look at Earth from space, you can see a lot of water. We are, after all, the blue planet. That means it must be very wet, right? At first glance, our world seems to have a lot of water. After all, 3/4 of it is made up of oceans. But that's not true. Only 0.06% of the mass of the Earth is water. Some water is on the surface as oceans, and some is stuck in the mantle. But actually, the Earth is a relatively dry rock. All of the inner rocky planets formed very close to the Sun, so they started off dry. Any water they might have had either evaporated or was blown away when things hit. These massive collisions that formed the Earth were so energetic that if there had been water here, it would have evaporated and left the Earth. So where did all the new water on Earth come from? It's not here. When you look at Jupiter, Saturn, Uranus, and Neptune, you can see that they have a lot of water locked up inside them. And even more dramatically are the moons. At least half of the water on the moons of Jupiter, Saturn, Uranus, and Neptune. A lot of water was out there. So how did some of it get to planet Earth? The answer is almost certainly that there were far enough from the sun that they could keep their water. There were millions of these watery asteroids and comets that flew into the inner solar system. Some of them crashed into our planet. Over time, the Earth got the water that used to be in the asteroids. This is what makes up the mass of water that now covers almost all of the Earth. Without surface water, there would have been no life. What about water that is too much? The oceans would be much deeper and cover the continents and even Mount Everest. And it's likely that the exact amount of water that the Earth has is what made it possible for us, Homo sapiens, to evolve into a technological species. About 4 billion years ago, a blizzard of comets and asteroids brought just the right amount of water to Earth. This is how the world we know today came to be, and it's possible that the same thing is going on somewhere else in the universe right now. There is a lot of water out there, that much is certain. The most common atom in the universe is hydrogen, and oxygen is one of the next most common. H2O will definitely be a very popular molecule, which is exactly what is happening in our universe. So water is everywhere in the universe, and we're finding that planets are too. But we haven't yet found another planet where water is liquid. More than 400 new planets have been found by scientists, but our world doesn't look like any of them. What we haven't found yet is a planet around another star that is about the same size, mass, and chemical makeup as Earth. So it remains an extraordinary holy grail for humanity to find other abodes that remind us of home. But we'll keep looking. We know that our galaxy alone has around 200 billion stars, and up to 40 billion of them could have their own planets. We are entering what will be called the golden age of planetary exploration. In the future, we'll start to really understand, for the first time, how different things are out there. I think this is going to be a very exciting time. The laws of physics and chemistry tell us how planets are made. Many scientists think it's only a matter of time before we find another planet like Earth, one that formed from the same materials in the right place with the right amount of water. One thing is certain, there are billions of planets out there waiting to be discovered. We inhabit a galaxy known as the Milky Way, which contains hundreds of billions of stars. How did we arrive at this point, and what is our future? These concerns involve galaxies in every aspect. The known universe contains 200 billion galaxies, each of which is unique, immense, and dynamic. Where do galaxies come from? How do they work? What is their future, and how will they die? If you are interested in amazing videos about the universe, be sure to subscribe to our channel to stay updated. This is the Milky Way, our galaxy, approximately 12 billion years old. The galaxy is a vast disk with enormous spiral arms and a central nucleus. It is only one of countless galaxies in the universe. Galaxies are massive assemblages of stars. First and foremost, a typical galaxy could contain 100 billion stars. They are actually stellar nurseries, the locations where stars are formed and perish. Stars in a galaxy are formed in nebulas, which are concentrations of dust and gas. Our galaxy contains billions of stars, many of which have planets and moons orbiting them. But for a very long time, we knew very little about galaxies. A century ago, we believed that the Milky Way was the only galaxy in the universe. In 1924, astronomer Edwin Hubble altered the entire situation. Hubble observed the universe using the most sophisticated telescope available at the time, the 100-inch hooker on Mount Wilson near Los Angeles. Far, far away, he saw hazy masses of light in the darkness of the night sky. He realized they were not even separate stars. They were entire star-filled cities, constellations far beyond the Milky Way. The astronomers received an existential jolt. We went from the Milky Way galaxy being the only galaxy in the universe to billions of galaxies in a single year. Hubble made one of the finest discoveries in the history of astronomy when he discovered that the universe contains a large number of galaxies rather than just one. This is the Whirlpool Galaxy, which comprises over 160 million stars and is characterized by two enormous spiral arms. In addition, the stars of the huge elliptical galaxy M87 shine with a golden hue since it is one of the oldest galaxies in the cosmos. And this is the Sombrero Galaxy, with its massive bright core surrounded by a cloud of gas and dust. All galaxies are very beautiful. They stand in for the fundamental building block of the cosmos. As they spin across space, they resemble a grand scale. On Earth, we measure distance in miles. In space, astronomers use light years, which is how far light can travel in a year. Our galaxy's diameter is over 100,000 light years, and we're now located at a distance of 25,000 light-years from its center. However, in the grand scheme of things, even our galaxy seems like a tiny dot. While the Milky Way seems enormous from Earth, when compared to other galaxies, it is really rather little. Andromeda, the galaxy closest to us, is about 200,000 light-years wide, making it twice as large as the Milky Way. M87 is the largest elliptical galaxy in our own cosmic backyard and much bigger than Andromeda. But M87 is tiny compared to this giant. IC 1011 is the biggest galaxy ever found. It's 60 times the size of our own Milky Way. It's common knowledge that galaxies are enormous and ubiquitous. But why is this the case? The origin of galaxies is a key mystery in astrophysics. Approximately 13.7 billion years ago, the universe began with, after the Big Bang, a period of intense heat and density. We know that there could not have been anything like a galaxy at that time, so galaxies must have come from that very early universe and formed from it. For stars to form and for galaxies to form from those stars, gravity is essential. After the Big Bang, the first stars began to emerge only 200 million years later. The earliest galaxies formed as their masses began to clump together due to gravity. Thanks to the Hubble Space Telescope, we can now see the early universe when galaxies were just beginning to form. Numerous galaxies are visible to the Hubble. However, the light we see from distant galaxies now actually departed those objects many millions or perhaps billions of years ago. What we see now is the distant past of those galaxies since it took so long for their light to reach us. The Hubble Deep Field reveals a collection of fuzzy dots, which are quite different from the galaxies we see now. We can hardly make out these little specks of light. Those fuzzy patches of light are really millions or billions of stars beginning to combine. The oldest galaxies are represented by these barely visible blotches. They began to take shape around 1 billion years after the Big Bang. However, Hubble's range of visibility ends there. A second sort of telescope, one too large to send into space, is required if we are to travel much farther back in time. Not only can the telescope identify primordial galaxies, but it can also trace their evolution. The evolution of galaxy and galaxy cluster formation may be followed. All the galaxies that have developed since the cosmos was just a few 100,000 years old are leaving their imprints for us to observe. Finally, scientists can begin to answer the question, what did young galaxies look like? Galaxies have evolved from clusters of stars to the complex web of systems we see today, and this process is being seen by astronomers. As far as we can tell, the greatest structures in the universe today originated as star clusters, evolved into galaxies, formed clusters of galaxies, and ultimately coalesced into superclusters of galaxies. There was a lot of stardust, gas, and clumpy structures in the early galaxies. However, modern galaxies seem organized and tidy. When and how can tangled clusters of galaxies become neatly organized spirals and pinwheels? Gravity is the explanation. Galaxies are molded by gravity, and its effects determine their fate. At the center of most galaxies lies an unfathomably strong and destructive gravity source, and our own Milky Way has one hidden at its core. Over 12 billion years have passed since galaxies first appeared. These stellar conglomerations may take many forms, from spirals to giant spheres of stars. As far as we can tell, however, there is still a great deal we don't understand about galaxies. How did galaxies evolve into their present forms? Did spiral galaxies always have to be spirals? The answer is almost certainly no. Young galaxies are a mix of stars, gas, and dust. They are untidy and chaotic. They begin as chaotic formations like the Whirlpool galaxy. Then over billions of years, they develop into more orderly, but from a cluster of several. Our Milky Way originated as a collection of disparate formations, objects of varying sizes and shapes that gradually merged to become the galaxy we see today. Gravity is what binds the various components together. Over time, it gradually draws stars closer. They pick up speed and flatten out into a disk shape. Massive spiral arms gather stardust and gas. This process was carried out countless times during the course of the cosmos. While visually distinct, these galaxies share the fact that they all seem to circle the same central object. For a long time, researchers pondered what might possibly alter a galaxy's behavior, and they found out a black hole, and not just any kind of black hole, but a supermassive black hole. The discovery of extreme amounts of radiation coming from the centers of certain galaxies was the first indication of supermassive black holes. Black holes in these galaxies are eating their surroundings, much like a giant Thanksgiving feast. The gas and stars are the supermassive black hole's dinner. Sometimes, black holes consume their food so rapidly that they spew it out into space as beams of pure energy. They refer to it as a quasar. The presence of a quasar indicates the presence of a supermassive black hole at the center of the galaxy. However, what about the Milky Way? There's no quasar here. Does it rule out the existence of a supermassive black hole? Observing the motion of the stars is the key to finding the supermassive black hole in the heart of our Milky Way galaxy. Like the planets that circle the sun, the stars also move due to gravity. We discovered that at the center of our galaxy, everything is more extreme. Things move very quickly, and the stars will be passing one another at high speeds. It is unlike any other place in the universe. The photographs of the stars in orbit showed a remarkable phenomenon. They had to have been traveling at 1,000,000 miles per hour or more. Only a gigantic black hole has the energy to toss large stars around like that. This curvature was the conclusive evidence for a supermassive black hole at the heart of our galaxy. As it is the black hole's gravity that drives the orbits of these stars, a massive black hole measuring 15 million miles wide sits at the heart of our Milky Way galaxy. So is there any danger to Earth? We are in absolutely no danger of being sucked into our supermassive black hole. It's simply too far away. In reality, the distance between Earth and the supermassive black hole in the heart of the Milky Way galaxy is 25,000 light years. That's many trillions of miles. For the time being, Earth is secure. Although supermassive black holes are the source of enormous quantities of gravity, they are not strong enough to bind galaxies together. In reality, the rules of physics dictate that galaxies should accelerate away from one another. So what's stopping them? Because there's something stronger than a gigantic black hole waiting to be discovered. Just like you did with the cake, then you put it in the oven and bake it, and it would change. So basically, this is what happened in the solar system. Overall, the planet cooks in a slightly different way depending on how close it is to the sun. Near the sun, where it is hot, gases are burned off and water boiled away. Only materials that stay solid at high temperatures, like metals and rocks, can survive. This is why only rocky planets form close to the sun. As a planet moves farther away from the sun, it cooks in a different way. But what kind of planets will form depends on what's in the cloud. Based on what kind of cloud a solar system forms in, it might not have any rocky planets because it didn't have enough materials to make something like Earth. Instead, it might have more gas giants or none at all. If you want planets that are made of rock, you need a cloud full of metals and rocks. The next step is to turn down the heat. As it cools, some of the things in it that have a high boiling point start to condense out as solids, and these very small mineral grains can start to form. These tiny pieces of rock and minerals are the beginnings of a new rocky world. They start to stick together over time. If you had one dust molecule and another dust molecule, they would basically hit each other and make one slightly bigger dust molecule. And they keep getting more and more. This process is called accretion. As these things got bigger, they became basically rocks. Then rocks slam into other rocks and form boulders. Boulders smash together to form bigger boulders. At some point, you'll have something big enough that its weight is strong enough to start pulling things towards it. So instead of just crashing into things and getting bigger that way, it was actively pulling things in. At first, there were a lot of young planets in our own solar system. If you maybe go to the asteroid belt and look at the asteroid 4 Vesta, you can get a good idea of how big a hard planet has to be before it can pull itself into a spherical shape. Vesta is only 329 miles across, which isn't quite big enough to be a sphere. To become round, a growing planet needs to be 500 miles across. Then it has enough gravity to crush it into a sphere. Any smaller, and it stays in an irregular shape. Every time a round baby planet crashes into something, it makes it hotter and hotter until it starts to melt. Gravity is now starting to sort the heavy things from the lighter ones. Lighter things tend to float up and form a crusty layer, while heavy things like most metals fall down and form a much denser core at the planet's center. Finally, the young planets are invisible and very difficult to detect. It's called dark matter, and it's everywhere. Supermassive black holes discovered by astronomers are found in the centers of galaxies and are responsible for the rapid movement of stars in their vicinity. However, they are insufficient to hold all the stars in a vast galaxy together. So, what does hold them together? It was a mystery until a maverick scientist proposed that something unknown was at action. Fritz Zwicky, a Swiss astronomer, pondered in the 1930s why galaxies clustered together. He reasoned that because they weren't producing enough gravity, they should be flying apart. However, the force of our own gravity was insufficient. Therefore, he deduced that it must be something that had never been discovered before, something that had never even been considered, and he called it dark matter. Fritz Zwicky was decades ahead of his time, and that's why he graded on the astronomical community. And this is a brilliant idea, but he was correct. You know, it's possible that individual galaxies are also held together by the mysterious substance the Zwicky dubbed dark matter. Galaxies rely on dark matter as a kind of protective framework that keeps them from collapsing and moving about. Now, scientists have discovered that dark matter does more than just bind galaxies together. It may also trigger their evolution. Scientists believe that after the Big Bang, dark matter started to cluster, and these dark matter clumps evolved into the galaxy's nucleus. However, the nature of dark matter is still a mystery to physicists. Weird things happen with dark matter. Since we don't know what it is, obviously it's not constructed from the same substance that humans are. You can't push against it. You can't feel it. However, it is likely everywhere. It's a ghost-like material that will pass right through you as if you didn't exist at all. Although our understanding of dark matter is limited, it seems to be abundant across the cosmos. That means there must be at least 6 times as much dark matter as regular matter, what humans are comprised of in the cosmos. Matter to the cosmos is undeniable. It's what makes galaxies form and stops them from collapsing. Even though it's invisible and undetectable, dark matter rules the cosmos. These galaxies seem to be completely alone. It's true, they are trillions of miles apart, but actually, they live in groups called clusters, and these clusters of galaxies are linked together in superclusters containing tens of thousands of galaxies. The Milky Way's place in the cosmos remains a mystery. If you look at the overall image, you'll see that our galaxy is associated with a smaller group of galaxies, including about 30 members in total, and that our galaxy and Andromeda are the 2 largest members of this group. Further observation reveals, however, that our galaxy is embedded inside the Virgo supercluster. Researchers are now making maps of galaxy clusters and superclusters to better understand the cosmos. Galaxies are the immense star empires. The shapes range from enormous balls to intricate spirals. The problem is that they are always evolving. When we stare out into the cosmos, it's easy to assume that our galaxy hasn't changed in eons, but that's not true. The Milky Way is a dynamic galaxy. Over cosmic eons, its basic nature has been changing. Galaxies don't only evolve, they move as well, and sometimes they run into each other. The 2 galaxies will merge over millions of years when they collide. This kind of collision occurs all the time in the cosmos. Our own Milky Way is no exception. We are on a collision course with the Andromeda galaxy, and that's terrible news for the Milky Way. At a speed of around 250,000 miles per hour, our Milky Way galaxy will collide with Andromeda in about 5 to 6 billion years. It's all over for the Milky Way galaxy. If you could look out into space, you'd see the whole Andromeda galaxy hurtling towards us at a tremendous rate of speed. As the 2 galaxies interact, they both become more and more disturbed and closer together. There will be a dance of death between They release clouds of gas and dust in all directions. As galaxies collide, their combined gravity rips stars from their orbits and launches them into the void. As we approach doomsday for the Milky Way galaxy, it would be spectacular. The 2 galaxies will ultimately pass through one another and merge into a single one. The Milky Way and Andromeda, as we know them, will cease to exist, and a new galaxy will be born. It will look like a whole new galaxy. There's no escaping what's going to happen. The question is, what does it mean for planet Earth? We may either be thrown out into outer space when the arms of the Milky Way galaxy are ripped apart, or we could wind up in the stomach of this new galaxy. Stars and planets will be pushed all over the place, potentially leading to the end of planet Earth. Galaxies will continue to collide, but eventually, this era of galactic cannibalism will pass. However, there is an even more destructive force in the universe: dark energy. Dark energy is a recently discovered cosmic power that pushes galaxies apart, unlike dark matter, which brings them together. We have limited understanding of dark energy and its properties. It behaves in a strange way, as if space itself contains tiny springs, causing things to resist and be pushed away from each other. In the far future, scientists predict that dark energy will overpower dark matter, leading to the expansion of the universe and the gradual drifting apart of galaxies. Ultimately, galaxies will die off, receding farther and faster until they become invisible. This process will take an extremely long time, even trillions of years. However, currently, the cosmos is thriving, and galaxies are creating favorable conditions for life. Our solar system's location in the galaxy's Goldilocks zone, neither too close nor too far from the core, is fortunate for the existence of life on Earth. If we were closer to the center, the radiation would make life impossible. If we were farther away, there wouldn't be enough stars to support life. Considering the vastness of the cosmos, there may be millions of stars in the cosmic Goldilocks zone, where conditions are suitable for life. We continue to learn new things about the universe, sometimes realizing that our solutions only uncover even greater mysteries. The exploration of the cosmos remains awe-inspiring. Our Milky Way galaxy and the galaxies beyond it are filled with wonders and endless possibilities. Mysteries and unanswered questions abound in the universe. Just 20 years ago, who could have predicted that we would identify the black hole at the center of the galaxy, or accept the existence of dark matter and dark energy? Our existence at this moment, on this planet, in this galaxy, with the ability to ponder and seek answers across the cosmos, is truly astonishing. Galaxies are born, evolve, collide, and die. The Milky Way is our fortunate home, a place where intelligent life thrives. Ultimately, our fate is intertwined with that of every galaxy, as they are the creators shaping our identities. Throughout the universe, there are strange and surreal paradoxes that challenge our understanding. From the mysteries of quantum mechanics to the mind-bending properties of black holes, the universe presents phenomena that defy intuition and challenge our perception of reality. To explore these concepts further, subscribe to our channel for amazing videos about the universe. Despite all that we know, it represents just 5% of the universe. The remaining 95% is composed of dark matter, 27%, and dark energy, 68%, which are mysterious components we have yet to fully comprehend. Scientists use these concepts to explain the peculiar observations we make about the universe. Dark matter, which doesn't interact with light or electromagnetic radiation, cannot be directly detected but can be inferred through gravitational effects on visible matter. Its composition remains unknown, with theories ranging from undiscovered particles to exotic objects like black holes. Dark energy, on the other hand, is a hypothetical form of energy that permeates space and drives the accelerating expansion of the universe. Its exact nature is unclear, but it is believed to be a property of space. To our knowledge, it has three spatial dimensions. Length, width, and height are the three dimensions that define space, along with the dimension of time, making a total of 4 dimensions in spacetime. However, some theories in physics, like string theory, propose the existence of additional dimensions, potentially up to 11 dimensions. These extra dimensions are believed to be compactified or curled up, too small to be observed at our scale. While they may exist, their effects on the 4-dimensional spacetime can only be inferred through their influence on observable physical phenomena. The idea of the multiverse theory suggests that our universe is just one of many existing alongside it. Each universe would have its own unique properties and laws of physics. This theory raises profound implications for our understanding of the universe and our place in it. It could potentially explain the fine-tuning of our universe to support life, known as the anthropic principle. If there are countless other universes with different physical laws, the chance of at least one supporting life would increase. Time is a challenging property to understand in our universe. It is often defined as a measurable period, a continuum without spatial dimensions. We perceive time as having a clear direction or flow, seemingly unable to travel backward in time. The passing of time is intertwined with the functioning of our universe. According to the Big Bang Theory, time began along with the rest of the universe approximately 13.8 billion years ago. It may not make sense to question what existed before time itself. In physics, time is considered a fundamental concept representing the progression of events from the past through the present and into the future. It is often represented as a continuous line or axis. Time is measured in units such as seconds, minutes, hours, and years. It is an essential component of the four-dimensional space-time continuum, which includes 3 spatial dimensions and 1 temporal dimension. The flow of time is typically described as unidirectional, always moving forward. The nature of time is still a topic of ongoing research and debate in physics and philosophy. Some theories propose that time is an emergent property that arises from the complex interactions of the universe's fundamental components, while others suggest that time is a fundamental property of the universe akin to space and matter. The arrow of time, which refers to the perception of time moving forward and not being reversible, is often associated with the second law of thermodynamics. In certain situations, particles can be instantly connected through quantum entanglement, even if they are located at opposite ends of the universe. Quantum entanglement is a phenomenon where 2 particles become correlated in such a way that the state of one particle is instantly correlated with the state of the other. While this might seem like a violation of the laws of nature, it is consistent with the principles of quantum mechanics. However, it is important to note that this does not allow for faster-than-light communication or the violation of causality. The no-communication theorem in quantum mechanics states that it is impossible to use entanglement to transmit information faster than the speed of light. Regarding the question of whether we are alone in the universe, there are at least 2 trillion galaxies in the observable universe, each with numerous stars and planets. It seems unlikely that Earth is the only planet with conditions necessary for life to emerge. However, the lack of definitive evidence of extraterrestrial life, known as the Fermi paradox, raises various potential explanations. These include the possibility that life is rare, that it is difficult for life to evolve beyond a certain point, or that intelligent civilizations exist but have not yet been encountered. The search for answers to these intriguing questions about the nature of time, quantum entanglement, and the existence of extraterrestrial life continues to fuel scientific research and exploration. A limited lifespan and self-destruct before they can explore the galaxy. It is also possible that we simply have not looked in the right places yet. Our current methods of searching for extraterrestrial life are still relatively limited, and more advanced techniques in the future could uncover evidence of life elsewhere in the universe. Does the self-reference problem distort our perception of the universe? We humans are also part of galaxies. Are we really neutral observers of the universe? When we explore the universe, we are both observers and the subject of observation. How can we pretend to be neutral when we are deeply embedded in what we explore? Could it be that this self-reference problem affects the way we look at the universe and gives us an overwhelmingly wrong impression? The self-reference problem is indeed a complex issue when it comes to our study and perception of the universe. We are not neutral observers of the universe, but rather embedded within it. This self-reference problem can lead to potential distortions in our perception of the universe, as we may unwittingly project our own preconceptions and assumptions onto our observations. For example, we may tend to focus on phenomena that we find particularly interesting or relevant to our own existence, rather than taking a more objective and comprehensive approach. By acknowledging our biases and limitations, we can work to develop more rigorous and objective methods of observation and analysis. Why is the universe seemingly so perfect for us? It seems to be perfectly made for us, but why is this? Why do the fundamental constants of our universe, such as the speed of light, have the values that they do, allowing life to exist? Could it be that there are infinite universes with infinite possibilities, and we merely happen to live in one that is perfect for life? There are a few possible explanations for this apparent fine-tuning of the universe. One possibility is the anthropic principle, which states that the universe is the way it is because it must be compatible with the existence of observers. In other words, the universe appears fine-tuned for us because, if it were not, we would not be here to observe it. This is sometimes referred to as the selection effect. Why is it easier to destroy something than to put it back together? Entropy is the amount of disorder, chaos, or randomness in a system. One can never reduce entropy. Everything in the universe slowly moves towards disorder. It's very easy to smash a window, but impossible to put it back together exactly as it was before. The principle of entropy moves the universe from structure to chaos, from an ordered state to disorder. What does this tell us about the fate of the universe? As the universe continues to expand, it will eventually reach a state of maximum entropy, where all matter is uniformly distributed, and there is no energy gradient available to drive further processes. This state is known as the heat death of the universe, where the universe will be cold, dark, and lifeless. The universe is not a closed system as it receives energy from stars and other sources, but the overall trend is towards increasing disorder and chaos. However, it is important to note that this process will occur over an extremely long timescale, likely trillions of years in the future. Can anything escape a black hole? We have observed the effects of black holes, and we have seen one directly. The gravitational force of these massive objects pulls everything towards them, even light itself. What happens in the mysterious, infinitely dense center of a black hole? Could there exist such things as white holes, the opposites of black holes that spew matter and time into our universe? According to our current understanding of physics, nothing can escape a black hole once it is past the event horizon, which is the point of no return. The gravitational pull of a black hole is so strong that it warps space and time, and anything that crosses the event horizon is inevitably pulled towards the singularity at the center of the black hole, where the laws of physics as we know them break down. We do not know what happens at the center of a black hole, as our current understanding of physics is unable to describe the conditions there. It is commonly believed that the matter at the singularity is infinitely dense and compressed to a point of zero volume, known as a singularity. As for the possibility of white holes, which are hypothetical objects that are the opposite of black holes, there is currently no direct evidence to suggest that they exist. Hypothetical objects that are believed to exist at the other end of a hypothetical wormhole, which is a tunnel-like connection between 2 points in spacetime. However, there is no direct evidence to suggest that wormholes exist. The universe is full of strange and surreal paradoxes, and our quest for understanding them is only just beginning. As we continue to push the boundaries of our knowledge and explore the furthest reaches of space and time, we can be sure that the universe will continue to surprise and challenge us in new and unexpected ways, spurring us on to new cosmos taking shape. Approximately 13.7 billion years ago, there are still many mysteries about how this came to be, or if there was ever a time before time. Physicists have pieced together an approximate timeline of significant events in the existence of the cosmos using telescope data and models of particle physics. From its beginning to its inevitable demise, we examine key points in the evolution of our universe. Welcome to the Endless Universe. If you are interested in amazing videos about the universe, be sure to subscribe to our channel to stay updated. The Big Bang is a moment in time, not a location in space. It represents the first second of time, the point from which all other seconds have been measured. The Big Bang was not an explosion, but rather a time when the universe was incredibly hot and dense before space began to expand outward in all directions simultaneously. The specific details of what happened at that time are still unknown, but we now understand that the cosmos broke down at the Big Bang because mathematical infinities don't make sense in physics equations. The next cosmic concept is cosmic inflation, where the universe rapidly expanded in size. This period, known as inflation, is still mostly theoretical, but has gained favor among cosmologists as a possible explanation for the striking similarity between distant parts of space. Attempts to detect this expansion in light from the early cosmos were reported in 2014, but further investigation revealed that interplanetary dust was causing the interference, not the expansion itself. After the Big Bang, the temperature of the early cosmos was incredibly high, between 7 trillion and 10 trillion degrees Fahrenheit, 4 trillion and 6 trillion degrees Celsius. In the first few milliseconds, quarks, elementary particles, were free to move about. They combined with gluons, carriers of the strong force, in a primordial plasma that pervaded the whole universe. This condition only lasted a few fractions of a second. The subsequent period, beginning a few thousandths of a second after the Big Bang, was a period of intense activity. The universe cooled as it expanded, allowing quarks to merge into protons and neutrons. Around 1 second after the Big Bang, when the density of the cosmos decreased sufficiently, the cosmic neutrino background was created. This background consists of neutrinos sailing across space without interacting with anything. During the first 3 minutes of the universe's existence, protons and neutrons fused together, creating hydrogen isotopes such as deuterium, helium, and a trace quantity of lithium. As temperatures settled down 380,000 years after the Big Bang, hydrogen and helium atoms could join with free electrons to form the first neutral atoms. This created the cosmic microwave background, which was first identified in 1965 and consists of photons flowing without disruption. After this period, there was a lengthy time frame known as the Dark Ages, when nothing in the cosmos emitted any light. The cosmic Dark Ages lasted for approximately 100 million years, during which astronomers could learn about the cosmos mostly by studying starlight. The origin of the first stars remains a challenge to study. They were formed when hydrogen and helium began to compress into massive spheres around 180 million years after the Big Bang, creating extreme temperatures at their centers. The neutral hydrogen atoms in interstellar space were broken apart into protons and electrons by the intense photons generated by early stars and galaxies. This marked the period known as cosmic dawn or ionization, which is hard to precisely determine due to subsequent gas and dust obscuring its signals. Scientists estimate that it was finished by around 500 million years after the Big Bang. Large-scale structure formation occurred almost a billion years after the Big Bang, with supermassive black holes developing at the cores of merging early galaxies. Intense quasars became visible from 12 billion light-years away and began emitting bright beams of light. Over the subsequent few billion years, the cosmos underwent further evolution, with denser regions in the early cosmos drawing more material due to gravity. The result is a beautiful filamentary cosmic web, which expanded into galaxy clusters and lengthy strands of gas and dust. About 4.5 billion years ago, a yellow star with rings around it formed from a cloud of gas in one galaxy. These accreted rings eventually became the 8 planets of our solar system, along with comets, asteroids, dwarf planets, and moons. Earth, the third planet from the Sun, retained a lot of water through this process or received a deluge of ice appeared on Earth between 3.8 and 3.5 billion years ago, which evolved into marine organisms and eventually large dinosaurs that fed on plants. Around 200,000 years ago, upright beings capable of contemplating the vastness of space and learning about the universe's origins emerged. The future of the cosmos remains a mystery. It depends on accurately quantifying the characteristics of dark energy, which is believed to be accelerating the expansion of the universe. If the universe continues to expand forever, all the stars will eventually burn out, and even black holes will evaporate. This would leave behind a lifeless cosmos filled with inert energy. Another possibility is the Great Crunch, where gravity overcomes dark energy's expansionary force, causing a reversal of the Big Bang. The Great Rip is also a potential outcome, where the cosmos tears itself apart due to accelerated expansion caused by dark energy. In summary, the study of the origin and future of the cosmos poses significant challenges, but ongoing research and exploration aim to unravel these mysteries. Desire to communicate with us. Ancient aliens theory suggests that aliens have visited Earth in the past and influenced human history and culture. Proponents of this theory point to ancient artwork and texts as evidence of alien visitation. UFO sightings or unidentified flying objects are often cited as evidence of alien visitation. While many sightings can be explained by natural phenomena or human-made objects, Some remain unexplained and could potentially be evidence of extraterrestrial visitation. Simulation theory proposes that our entire reality is a computer simulation created by an advanced civilization. While not specifically about aliens, this theory suggests that the creators of the simulation could potentially be an extraterrestrial civilization. Do aliens exist? According to the Drake equation developed by astronomer Frank Drake in 1961, the probability of intelligent life existing elsewhere in the universe is high. The equation takes into account factors such as the number of stars in our galaxy, the number of planets that could potentially support life, and the probability of life forming on those planets. Using these factors, the Drake equation estimates that there could be millions of intelligent civilizations in our galaxy alone. However, there is little concrete evidence to support claims of encounters with these civilizations. What might aliens look like? The traditional image of small, green, big-eyed aliens is a product of popular culture. In reality, their appearance would depend on the conditions of the planet they evolved on. For example, gravity and environmental factors could influence their physical forms. Why would aliens visit Earth? Some scientists speculate that aliens might be interested in studying our planet due to its unique location in the universe and its ability to support life. Another reason could be their attempt to make contact with us if they are trying to communicate with other intelligent civilizations. However, their methods of communication might be vastly different from ours. If we encounter aliens, caution should be exercised. Scientists believe that we should approach any encounter peacefully and non-threateningly, attempting to communicate in a way that minimizes misunderstanding and misinterpretation. The solar system formed from a cloud of gas and dust. Planets closer to the sun are rocky, while those farther away are gas giants. Different clouds can form different types of planets. Small mineral grains begin to stick together and form rocky worlds. As they grow, rocks collide and form boulders. Gravity pulls material towards them, shaping them into spheres. Some planets didn't survive, but the ones that did became round. When baby planets collide, they melt and form layers. Lighter materials float up, while heavier ones sink to the core.